In this lecture, we review the algebra of exponents. Before we can be successful in science and calculus, we need some comfort with algebra. Here are two major algebra computations we will do throughout this class and you will do throughout your career: exponential notation and polynomial arithmetic. Here we review exponential notation. About 3 centuries ago, scientists developed abbreviations for multiplication of a variable, replacing x times x by x squared, x times x times x by x cubed, x times x times x times x times x by x to the fifth, and so on. This is just an abbreviation. The exponent merely counts the number of times the base x appears in the product. This leads to some basic rules consistent with the abbreviation. For example, if we multiply x cubed times x squared, then what we really mean is x times x times x times x times x, which is x to the fifth, since there are 5 x's involved in this multiplication. So if we multiply objects with the same base, we should be adding the exponents. In the same way, x cubed divided by x squared is x times x times x divided by x times x, and we can cancel out 2 of the x's, top and bottom, to get x, and so when we divide objects with the same base, we subtract the exponents. Finally, if we took x cubed and squared it, well, x cubed is x times x times x, and when we square that, we have x times x times x times x times x times x, or x to the sixth. In other words, repeated exponentiation leads to multiplying exponents. So we have 3 rules here that come out of the abbreviation. When we multiply 2 elements, we add the exponents. When we divide the elements, we subtract the exponents. And repeated exponentiation leads to multiplying exponents. Our symbolic abbreviation involving exponents leads to these basic observations, sometimes called algebra rules. Here are a few more. Notice that multiplying by 1 leaves the number unchanged, but also if we do our computations x to the n times x to the 0 and add our exponents and get x to the n, we notice that multiplying by x to the 0 leaves the number unchanged. Multiplying by 1 leaves the number unchanged. Multiplying by x to the 0 leaves the number unchanged, so x to the 0 must be 1. We can also extend our exponent notation to rational exponents. Since x to the 1/2 squared, when we multiply our exponents, should give us x to the 1/2 times 2, which is x to the 1, which is x, then x to the 1/2 has the property that when you square it, you get x. So x to the 1/2 must be the square root of x. More generally, denominators and exponents represent roots. X to the 1 over q is the qth root of x. Let's practice this with 2 exercises. We'll simplify 8 to the 2/3. 8 to the 2/3 can be thought of as 8 to the 1/3 squared. And 8 to the 1/3 is the cube root of 8. So we have the cube root of 8 squared. But the cube root of 8 is 2, so 2 squared is 4. We could simplify 4 to the 3/2. Think of 4 to the 3/2 as 4 to the 1/2 cubed. The exponent 3/2 is being broken into 2 pieces, the product of 1/2 and 3. But 4 to the 1/2 represents the square root of 4. So we have the square root of 4 cubed, or 2 cubed, which is 8. Here's a problem common in computer science applications. Note that 2 to the 10th is 1024, while 10 cubed is 1000. So 2 to the 10th is about 10 cubed. The electronics of a computer means that computer scientists work in base 2. Computer storage and computer memory is measured in powers of 2. But the language of computer science uses traditional human powers of 10. Kilo represents 1,000, mega a million, giga a billion, and so on. But to a computer scientist, kilo probably represents 2 to the 10th, not 10 cubed. Computer scientists approximate powers of 2 as powers of 10. For example, we might approximate 2 to the 30th as a power of 10. Since 2 to the 30th, by our laws of exponents, is 2 to the 10th cubed, and since 2 to the 10th is about 10 cubed, then 2 to the 30th, which is 2 to the 10th cubed, is about 10 cubed, which is 10 to the 9th. How many digits are there in 2 to the 300th? Let's write 2 to the 300th as 2 to the 10th to the 30th. Replace 2 to the 10th by 10 cubed, so we have 10 cubed to the 30th, and get about 10 to the 90th. Now 10 to the 90th is 1 times 10 to the 90th, or 1 followed by 90 zeros. So 10 to the 90th has 91 digits. So 2 to the 300th should have 91 digits. If we type this into Wolfram Alpha, we get this number. There's 2 to the 300th. You can check. It has 91 digits. To succeed in calculus, we need comfort with these algebra techniques. Practice these techniques throughout the semester so that you can indeed be comfortable with your algebra. In the next slide presentation, we practice problems involving exponents and polynomials.